We had already talked about the Lagrangian and Euler-Lagrangian equations for the fields. Now we will talk about Hamiltonian, and we will see what it means for the purpose of the fields. Now, in general, we think that Hamiltonian is energy. Now, Hamiltonian is in quantum mechanics, it acts like an operator. In classical mechanics, it is just another cousin of Lagrangian, and you have the Hamiltonian equations, which can give you the equations of motion for the field, and everything can be known based on that. Energy is, of course, represented by the Hamiltonian, but Hamiltonian by itself is not just energy. So it is something, there is something more to the Hamiltonian rather than just being called as the energy. Then you saw that there is a formulation for the field in case of the Lagrangian, and for particles we have one kind of Lagrangian, then we have the Lagrangian equation giving rise to the fields, then we have a correspondence from the particles to the fields, and when we transit from the particles to the fields, then we have the notations for the Lagrangian density, and there is some kind of alteration that we have to make in order to fit the Lagrangian formalism within the field theory. Similarly, the Hamiltonian for the particles is, as you know, represented as H is equal to P V minus L, right? Where, you know, P is the canonical momentum and V is the generalized velocity, L is the Lagrangian. So this holds for the case of the particles very well. In case of the fields, you have to make certain kind of generalizations, and those generalizations stand like this. In place of P, which is the canonical conjugate momentum, in place of P, you write something else that is in form of this del L by del of generalized velocity. Now, generalized velocity here will be something like the field coordinate, which in general is phi k, and I am just taking the derivative with respect to time. So this thing in the bracket del phi k by del t is the generalized velocity, and then we write here v, and for v it is just this thing. So it is phi k and t, right? Minus, right here L. Now what should be this L? L generalized should be given as something called the Lagrangian density. So better still, you should, at this stage, you should write down this thing as the Lagrangian density, right? On the left, we have defined a quantity which is the Hamiltonian density. So the first case refers to the particles, and the second case refers to the fields, right? And you can see how the things are generalized when we go from the particles to the fields, right? We should also realize that we define the Hamiltonian density just as we define the Lagrangian density for the fields, and we have the same rule working, that for fields we have H given as d3x, that is the volume integral of the Hamiltonian density. And here we know that this in H is a representation of the total energy of the system. And last time I told you that this total energy of the system is actually a time component of the 4 vector P naught, right? Time component of a 4 vector. So it is like P naught. And on the right hand side, this d3x is something again like a time component. And then we can say that this h is like time component. Okay. So let us explore this. What is the nature of this, and what is the nature of this Hamiltonian, right? Try to write it down as follows. This d3x is the volume element of spatial region, right? dx1 into dx2 into dx3. So what we do is we see that this d4x on the other hand is Lorentz invariant. We all know that this is Lorentz invariant quantity. That is, this is a scalar of rank 0, right? And just now we saw that when you write it in form of the dx naught and d3x, then you can identify the second part, that is d3x, as the time component of some vector. Let's see how. You see, this is a scalar quantity. d4x is a scalar quantity. So any scalar quantity can be written as di and di. Okay. So you write here di. And what is it? If you open it, you find that this is d0, right? Plus d1, okay, plus d2 and d2, and d3 and d3. Okay. Now, if our 4 volume is like di, and di has all these components, but here in our expression on the right, we have only this. So this expression tells us that it is the first part of this. That is d0. Okay. So it can be written as what? It can be written as d0 and d0. Okay. My purpose is to identify the nature of d3x, right? And from this simple argument, it appears that this d3x seems like d0, right? So it is like d0. What about the rest of the components here? The rest of the components here are all absent in our present case of d4x. So the lesson drawn from this is the following. The 3 volume of the region goes like d0. Okay, that is the time component of a covariant 4 vector. Now, having said this, we return to our earlier expression that this H for the field is the Hamiltonian density times d3x and the integration of it. And we just saw that this H Hamiltonian is equivalent to energy, and this is like time component of a 4 vector, right? On the right, we can now see that this d3x is like d0, that is time component of another 4 vector. Now, if we have to balance this equation, this H should go something like, you can say theta, okay? And then let us play the trick of balancing an equation by simple tensorial considerations. Okay, how do we balance it? The 0, which is in d0, the 0 should appear here to make it compatible, the 0, 0. And this 0 over p should act like a free index, and that should go here. Okay, so in this way, we have now affirmed that this Hamiltonian density is like theta 0, 0, or in other words, the Hamiltonian density is a particular component, time component of a tensor of rank 2. So we can write that this Hamiltonian density, let's call this a density, okay, don't forget this. So Hamiltonian density is the covariant, or rather is the time component, TT component of a bigger tensor. The bigger tensor is theta ik. Okay, when you write time component, you mean theta 0, 0. And we have just seen that Hamiltonian density or the energy density is the time component of a bigger tensor of rank 2, that is theta ik, right? This theta ik is very important, and we will be soon calling it as the canonical stress tensor. So in our next slide, we will talk about this theta ik, right? And this is called the covariant generalization of the Hamiltonian density, right, for fields. Okay, how do we define it? Now this is called the canonical stress tensor, right? In short, it is called CST, and we can define this CST as follows: theta ij, because it is a tensor of rank 2, we have just obtained, because we want to define the energy for the field. And then you write it as the following, and see that everything should be properly balanced with the tensorial terms. So del IAK, and above it, it goes del JAK. Okay, all of you should be in habit of writing it out properly, and GIJ and L. Okay, so this is how we have defined this quantity, and you know that this L for the free fields can be put here, because we know its value, minus 1 upon 16 pi FIK, right? So using this value, we can go back to our canonical stress tensor, and then we can write down this expression. We have not considered the source term in this, source contribution in this, so it is just for the fields alone. The whole formalism will work for the fields. Let us calculate the first term, okay? And since we have some practice of doing it, as I gave you in a problem in my earlier lectures, how to find this expression in the red box here. It is del IAK, and you have this whole thing. So put L there for the free fields, okay, and just calculate it. Since we have already done this exercise, so I will write down what the answer should be. So please do this. So the first part will become minus 1 over 16 pi, which comes from the Lagrangian, and then you have 4f, right? And this ik, look here at the denominator. This is del IAK, and I is a covariant index in the denominator, so it should go up here, and k is the contravariant index, so it should go down. So we should write it like this, and then the whole thing. Okay. Now, if you like, you can further write it a bit in a different way. That is this whole thing, minus 1 over 16 pi, and the 4 they get cancelled. Of course, you get then minus 1 over 4 pi, right? And this FIK, this Fik can be written as, you can take this index down by again using that metric tensor. So you can write this as Im and Mk. Okay, this is more beautiful because now you have Fmk, the field strength tensor, both the indices are sitting in the covariant positions. Okay, so then you can plug this thing back here and write down the whole expression, and then you write the following. So theta ij will be minus 1 over 4 pi, and I said gim, and then you write mk, easy to remember. And then you write here j, this j comes from theta ij, and then this ak, which is the field coordinate, right, minus gij and l. Okay. Okay, so this is perfectly all right, and we know that the 4 divergence of this particular quantity has to vanish. Okay, so this is an important thing which everyone can do, that the 4 divergence of this should vanish. That means if you calculate del I, ij, the answer should be 0. Okay, so I hope that you would be doing it today. This thing. It is very simple, hardly a 3-line expression, but I want you to do it. Also, little further, if you search for the other properties of this tensor, then we will find that, I hope you remember this from your earlier semester, plus something. Okay, so that means that it is not equal to the energy density. Okay, also its other components like time space components, theta 0 mu, are density. Okay, so in a way, when we will talk about the 0 component and 0 mu, 0 1, 0 2, 0 3 components of this tensor, then we will not be able to attach any specific physical meaning to them in terms of the energy density or the momentum density, and that is one of the failures of this tensor. So I will quickly revert to that, but before that I give to you this thing as a problem to show, right? Consider for source-free case. Don't take any sources, don't include any j's. Just find out theta 0 0 and theta 0 mu. Okay, and you can revert to me on WhatsApp, on my email as well, and then we can solve these issues further. But it is sufficient for me to say that this theta ij is not good for us. It is not good for us. Although we have determined this kind of a tensor as the generalization of the Hamiltonian density for the fields, but it is still not good. And the reasons are twofold. One is that it is not a symmetric tensor. Again, a thing which can be checked, that it is not symmetric, right? And you know the property of a symmetric tensor, that theta ij should be called a theta ji. So if you change the indices, the answer should be the same. But it doesn't happen for this, and you should actually check this, right? So it is not a symmetric tensor. And I will tell you why the symmetry of a tensor is required tomorrow. I will tell you while talking about the angular momentum, right, and other things. But for today, it's enough to say that this is not a good tensor because it is not symmetric. And number two, its components are not physically meaningful. As I just showed that the 0 0 component cannot be called as the energy density, or 0 mu component, 0 1, 0 2, 0 3 component cannot be called as the momentum density. So the components are, I should write here, the components are not physically meaningful. Okay, physically meaningful. So we will hit upon something else. The good side, of course, is that its 4 divergence vanishes, as I just gave you as a little exercise to do that theta del I theta ij should be equal to 0. You can show it. So it's a plus point that it is nice. But these two things, that it is not symmetric and the components are also not meaningful, physically meaningful, that thing, something is not satisfactory to us. And that's why we move forward in our journey and try to find a better tensor. That better tensor, I will talk to you tomorrow about, is Tij, or we will call that as energy momentum tensor. Energy momentum tensor, right? And we will define it tomorrow. So don't worry. It is called energy momentum tensor and also called stress energy tensor or stress energy tensor, right? So if you have any questions, I have to close this meeting today in just this much time. But if you want to ask me something, you're welcome. You can switch on your microphones and you can talk to me. Yes.
Hello.
Yeah. Go ahead.
Sir, in your slides, when you write Hamiltonian in terms of Hamiltonian density equals to integration Hamiltonian density d3x, then how do you relate this expression as P0 equals to theta 00 d0? Please explain again.
So when I said this H is equal to the Hamiltonian density and d3x, right? You know that this H on the left hand side, the total energy is like the time component of a 4 vector, right? It is not a scalar by soon, because you know the 4 momentum we defined as P0 is equal to, sorry, the 4
E by
momentum,
C.
right? Hey, just one sec. So the 4 momentum we defined as Pi is equal to P0 and the 3 components of the momentum. Okay.
Yes, sir.
In case of particles, we called it relativistic momentum of the particle. In case of the fields, you have the conjugate momentum of the particles and fields. Okay. Now, this thing, this P0 was energy divided by C.
Yes, sir.
So this is like, so it is energy by C. So it is, this H is like P0, the time component. And then I told you that look at this D3X. Okay, I gave you some argument to establish that this thing goes like D0. So go back to my slide to understand this. Okay. Now, once you know that it is D0, then look at this Hamiltonian density inside the integral, and you will see that this D0 you must have something like 0 here, so that this covariant index here is balanced by a contravariant index on the upper side, so 0, 0. But this is not enough. The complete story will be when you will take care about this free index. So this free index should be here, appearing here, that is H00, right? So overall, let us not call it H. We can call it by another symbol. And I use this notation for theta, calling it theta. And then I said that, okay, this looks at theta 00. And more carefully, this this blue 0 is coming from P, right? And the red 0 is coming from here. Okay. Let me again write it. The blue 0 here. Okay. So can you see this? The blue and red?
Yes.
Right?
Yes, sir.